Hello, sir. Good morning, sir. Hello, sir. Good afternoon, sir.
ஹலோ சார், இன்னும் மைக் கனெக்ட் பண்ணேன்னு நினைக்கிறேன் சார்.
சார் ஸ்டார்ட் பண்ணிடலாமா சார்?
சார், அவரோட மைக் கனெக்ட் பண்ணணும்னு நினைக்கிறேன். கொஞ்சம் அவருக்கு கால் பண்ணி தான் சொல்லணும் சார்.
சரிங்க. சார் சார் உங்க மைக் பேசுறது கேட்க மாட்டேங்குது சார். சார் மைக்கு கனெக்ட் ஆகல சார். உங்க மைக்கு நீங்க பேசுறது கேட்க மாட்டேங்குது சார்.
Hello. Hello. Am I audible?
ஹலோ சார்.
Hello. கேக்குதுங்க.
ஓகே சார்.
So all right, we have 24 participants. So how many of them are totally?
Sir, at now 24 sir.
Now 24.
ஆமா சார்.
Total எவ்வளவு பேர் சார்?
இல்ல வராங்க சார். வந்துட்டே இருக்காங்க சார்.
Okay, fine. We can wait, no problem. So இது எப்படி ஒரு 1 hour presentation அதுக்கு அப்புறம் டிஸ்கஷன் அந்த மாதிரிங்களா?
ஆமா சார், அது மாதிரி தான் சார். பார்ட்டிசிபென்ட் சாட் பாக்ஸ்ல அவங்களோட क्वेश्चंस கேட்பாங்க சார்.
அது எப்படி நான் பிரசன்டேஷன் பண்ணும்போது சாட் பாக்ஸ்ல நான்
இல்ல முடிச்சிட்ட பிறகு சார், டாக்லாம் முடிச்ச பிறகு சார் லாஸ்ட்ல.
ஓகே ஃபைன். சோ அப்போ நம்ம டைரக்டா ஆடியோ क्वेश्चन ஆன்சர்
ஆடியோ இல்ல சார்.
ஓகே ஃபைன்.
ஸ்டார்ட் பண்ணலாமா சார்?
ஓகே. ஸ்லைட் ஷேர் பண்ணனும் இல்லைங்களா?
ஓகே சார். சரிங்க சார்.
Screen
இப்போ உங்களை பற்றி ஒரு இன்ட்ரோ கொடுத்துறேன் சார். இன்ட்ரோ கொடுத்த பிறகு ஸ்டார்ட் பண்ணிக்கலாம் சார்.
Oh, sure.
ஓகே சார். Good afternoon, all of you. So once again, I welcome on behalf of PG and Research Department of Physics, Jamamum College, Trichy. So today we have second day of online faculty development program on spectroscopic techniques. So today our resource person, Dr. P. Tamilarasan, scientist and assistant professor, electronics and electrocatalysis division, CSIR, Sikri Karaikudi. He completed his PhD degree from IIT Madras in the year 2014. His main research areas are organic electrochemical transistors and spectrochemistry. Next, second one, bioelectrochemical devices and microbial electrochemical systems. He completed his postdoctoral fellow from King Abdullah University of Science and Technology, Saudi Arabia. He received Best PhD Thesis Award in Energy Applications from IIT Madras in the year 2014. He received the award of Invention of Impeccable Glucose Biosensor, which was widely recognized by national media. He received Invention Award from Intellectual Ventures, USA. He is a member of Society for Advancement of Electrochemical Society and Technology. He is a member representative in Electrochemical Society, USA. He published 24 papers in reputed international journals, including Nature Materials, Small, JMCA, JPCC. He filed a US patent on hydrocarbon protection from carbon dioxide. He is having 3 sponsored projects and completed 1 sponsored project. So with these brief introductions about our today's resource person, I invite our resource person to deliver a lecture on a plasmon assisted Raman spectroscopy. Okay, sir. Over to Tamilarasan.
Okay, Professor, thanks for your nice introduction. I'll go for sharing my slide. I think it's better to go with share my screen. Yeah. Okay, is it visible, sir?
Yes, sir.
Okay. How can I can minimize it here? Okay, good going. Very good afternoon, everyone. It's been almost 4, so very good evening, everyone. I hope this day was very good for you all. Sir, Professor, is it going to be an interactive session or just a one-way presentation?
Your way, sir.
Okay, anything is fine for me.
Okay,
anyone
sir.
can interact, anyone can stop me in between if you have any doubt or if I'm going inaudible or going very fast. You can stop me anytime and you can ask your questions. Anyway, very good afternoon. And today, in this fine evening, we will discuss some aspects of plasmon-assisted Raman spectroscopy. I will just start with some fundamentals. I don't go very deep because Raman spectroscopy is very known to most of you. As Professor Sheikh said, it's going to be a faculty development program. So talking about too much of Raman spectroscopy may not be appropriate here. I will just start with some fundamental and I'll go for what is plasmon-assisted Raman spectroscopy and so on, and then I'll discuss some of its recent applications, and I will finish it with the challenges and future opportunities in this technique. By the way, as the professor introduced, I'm from CSIR Sikri and I'm working as a scientist here, and I'm also affiliated to ACSIR as an assistant professor. And my work is mainly on spectral electrochemical techniques. Why it is not going to. So just to start with Raman spectroscopy. As we also already know, Raman spectroscopy is a Rowe-Brownick spectroscopy. It deals all three major spectroscopy techniques like rotational spectroscopy, vibrational, and an electronic spectroscopy. When you illuminate a sample with photons in Raman spectroscopy, it actually transfers from one electronic level to another one. And even in that electronic levels, it goes from one vibration level to another vibration level. Even in that vibration level, it goes very specific to one rotation level to another rotation level. So this leads to boundary conditions of del J plus or minus 2, because the rotational transition is coupled with a photon. A photon is a spin 1 particle, so you will end up with 1 plus 1, 2 photon interaction. One is the interacting electron, one is a scattered electron. So photon. So 2 photon crosses, so you'll end up with plus or minus 2. And the vibrational transition, that is molecular vibration transition, will have a plus or minus 1. Fine. And as I said, it is a 2 photon process, so it's a second order process. What is the difference between the Raman spectroscopy and IR spectroscopy? As we all know, IR spectroscopy is called molecular vibration spectroscopy, and of course Raman spectroscopy. Though it is called Rowe-Brownick, we always concentrate on vibration spectrum application of Raman. Why? Because the electronic is too far away. It's not going to give any new information other than our spectrophotometry, and the rotational level, nothing but the microwave level, will not be observed that clearly. It will be like a fine structure of our Raman spectrum. So the observable limit will be in the vibration spectroscopy. That's why in many publications you will see molecular vibration spectroscopy. Raman spectroscopy is designated as molecular vibration spectroscopy rather than these two. And for an IR spectrum to be active, we have some boundary conditions where the molecule should have a net change in dipole moment. What does it mean? As per the classical theory, if you want to emit a radiation, only an oscillating dipole can emit a radiation. So that is as per the classical theory. So to be active, it should have a net dipole moment, and that dipole moment should change. That means the molecule should vibrate. So that is the boundary condition. So if you take some molecules like carbon dioxide, of course carbon dioxide is active in IR spectroscopy, but not all the modes. If you take a symmetric vibration, symmetric stretching vibration, that mode is not active in IR mode, because there will be no net dipole moment. So because of that, you cannot detect the symmetric stretching of carbon dioxide using IR. But Raman is active. Why? Because for Raman, you no need to have a net change in dipole moment. You just have to slightly distort its electron cloud. That is sufficient enough to give a Raman scattering act. For that, you just have to have a net change in polarizability, that d alpha by dq should be non-zero, and that will induce a dipole moment into the molecule. So it is not the intrinsic dipole moment, it is an induced dipole moment. Because of that, you will get obviously a dipole moment, and it will also oscillate, because it is there is a net change in the polarizability, and that will emit a radiation. So with that, if you see this picture, you will, for most of you, this is very familiar. For a photon scattering with the electron cloud will lead to 3 different spectra. The first one is Rayleigh. Rayleigh is completely an elastic scattering, where the energy of the photon will not change. It will not lose, neither lose nor gain energy. The second one is these two are called Raman scattering, where the energy of the photon will change. If the photon gains energy, it is called anti-Stokes. If the photon loses energy, it's called Stokes. And generally, we use anti-Stokes lines for Raman spectroscopy measurements. Fine. If you see the theory, the probability of Raman scattering is at very low. It ranges from 10 power minus 4 to 10 power minus 6 based on its scattering cross section. That means to get one Raman active photon, you have to scatter 10,000 to 10 lakh photons on the molecule. So it's very low probability. So whatever the Raman signal you are getting is very less. When you wanted to go for say a trace amount of molecule detection or single molecule detection, definitely Raman spectroscopy will not allow that easily to detect such a trace amounts. So how can we enhance the intensity of Raman signals? Let's see this equation. It is the degree of polarization is equal to alpha E. Alpha is the polarizability of any molecule, and that is a so-called intrinsic quantity. Without any perturbation, it will not change. So it's an intrinsic quantity. The second, so we don't have much control over this one, but that's not completely true. I'll get back to this point later. And the second one is the E, the electric field. Whatever the applied electric field has very good control over with us. So playing with these two characters, how can we enhance the intensity? Let's see in the forthcoming slides. Uh, if you consider the Raman signal intensity, just consider this equation. Here the Raman intensity is proportional to the incident intensity. That's obvious. But we have other factors like the scattering cross section and the solid angle and so on. But very importantly, the intensity is proportional to the number density. Number density is nothing but how much of the molecule has been interacted with the electric field. So how to increase the number density? You have to obviously increase the electric field. So how to increase electric field? Let's see here. Can we, anyway, we know our electromagnetic spectrum has an electric component as well as a magnetic component. If you increase the energy of this electromagnetic radiation, obviously your electric component will be high. But how far we can increase? That's very difficult. You cannot increase the power too much. It will, at the end, it will burn your sample. So you should not increase the total power of your spectrum, but you need to increase the electric field. How to do that? If you see the enhancement is proportional to e power 4 law. So this I may discuss later. Let me introduce another fundamental topic here. It's called a localized surface plasmon resonance. As you all know, the surface plasmon resonance is nothing but the collective oscillation of surface electrons due to the interacting electric field. For example, if you throw a beam of light on a metallic surface, the metallic surface electrons, conductive electrons, will interact with the electric field of electromagnetic radiation, and they will oscillate and resonate at the frequency of your electromagnetic radiation. And for that, the metallic surface should have interface with a positive refractive index medium like air. Generally, metals will have negative refractive index. So because, when these conditions are satisfied, you will have surface plasmon resonance. Now, of course, each surface plasmon will have its own propagation length. It will start at the point of the interaction of the photon, and it will start propagating till it is completely dying. So it has its own propagation length. Now, if you wanted to confine them, if you wanted to confine this surface plasmon resonance, then you have to reduce the particle size or the plasmonic surface size. So instead of going for a complete flat surface, you can go for nanostructured surface. When the nanostructure size is smaller than the complete SPR propagation length, then the SPR will be confined. So when it is confined, there will be an enormous amount of electric field enhancement at that close vicinity. So that electric field can be used to enhance Raman spectrum. And secondly, this is one point. It is LSPR localization of a surface plasmon. If you put two LSPR activated particles together, when you brought them close to each other, then they will start interact. These two LSPRs will start interact. They will couple at some distance. When they couple, the electric field enhancement will be several times higher than what you are getting for a single particle. With this LSPR coupling, theoretically we can go up to 10 power 15 times. Experimentally, they have observed 10 power 8 to 10 power 10 times electric field enhancement. And also, this coupling has some fundamental say characteristics. Like if you have radiation in this direction, like in the coupling axis direction, then the enhancement will be very less. When it is perpendicular to the coupling action, direction, you will get a lot of enhancement here. So that is what we are saying here. When you couple particles and or when you illuminate the light on this substrate, you should illuminate from the top or bottom, like the perpendicular to the coupling direction. And I just wanted to go quickly with the history of surface enhanced Raman spectroscopy. In 1970s, the group of three scientists, Fleischmann, Hendra, and Jim, they started to work on understanding the metal organic interactions from the University of Southampton using Raman spectroscopy. Accidentally, they found in 1974 when you observe a pyridine molecule on silver, roughened silver substrate, they found the Raman signal has been enhanced several times. And they attributed this to the surface area enhancements. Because of the roughened surface, the surface area is surface area of silver is enhanced. So because of that, the number of molecule adsorbed is enhanced. So they got better Raman intensity. So that is what they had attributed. But in 1977, Professor Van Dune from University of Northwestern University, he thought, he found that the enhancement is almost 10 power 4 to 10 power 6 times. That means 10,000 to 10 lakh times. So he thought it is not simply possible because of the surface area enhancement, because the surface area will not be enhanced 10 power 4 to 10 power 6 times. So this is something beyond that. So he proposed a mechanism for electromagnetic enhancement, where he claimed that because of the electric field enhancement at the close vicinity of these particles, the Raman scattering is enhanced. And in the same year, there was another group from another group of scientists, Albrecht and Creighton. They have proposed a chemical mechanism. I'll explain what is chemical mechanism. But if you see this equation, we have seen already this. So the alpha is, I said it is an intrinsic quantity, and we have less control over this, but still this can be used for enhancement. And the electric field is for electromagnetic enhancement. The electromagnetic enhancement will be generally on the order of 10 power 6 to 10 power 8, and the chemical enhancement will be on the order of 10 power 2 or less in general. Let me explain what is the chemical enhancement here. As I already said, it is something to do with this polarizability of the molecule, that is alpha. We always know the bigger molecule will have a bigger electron cloud, and it gives more probability for the scattering per molecule. And if you have lone pair electrons, then once again you have higher electron density, that also will have better scattering probability. But the third one is injection of charge. That means you are actually increasing the charge density of your molecule by injecting electron from outside. Because of that, the electron density will be higher, and the polarizability, and thus the induced dipole moment will be higher, so that you will get a higher Raman intensity. These also have two different mechanisms. One is the charge transfer mechanism. As we have seen here, you have to have electronic transition to get a Raman spectrum, that is for sure. So if you take this structure, you have a HOMO and LUMO. If you put your Fermi level in between this HOMO LUMO, this Fermi level is for the metallic surface. So what will happen? The transition of the electron from HOMO to LUMO will be through this Fermi level of the metal. So it will assist the electronic transition. Because of this, you will get higher you will get higher Raman signal. The second one is metal complex formation. So you have already metal, your molecule may form a complex-like structure. It's not actually a chemical complexation, it's a complex-like structure where only the electron cloud of your metal and your molecule will interact to form an apparent increase in electron density that will increase the polarizability of the molecule. So having this, we will go for the fundamentals of the CERS substrate. What are the basic properties? What are the basic properties we have to look for to get a higher enhancement factor? Generally, these CERS substrates are made up of metal, particularly a noble metal like silver, gold, copper, or sometimes aluminum. Aluminum has some limitations because its surface will be very fastly oxidized. So, like these metals have been used. And as I already said, you will have localized surface plasma. If you put two particles together, there will be a coupling. So that means you should put two particles. Can we put two particles touching each other? No. Why? Because your LSPR, localized LSPR, will try to propagate with the other particle. So when these particles are effectively touching each other, you will lose the electric field enhancement. So they have to be separated at some distance. What should be the typical separation? A group of scientists have simulated this. They took a 100 nanometer particle and they have illuminated with light. And with respect to the distance, they calculated the enhancement factor. When the distance increases, the enhancement factor falls like exponential pattern. So at almost 150 nanometer, you're almost ending up with one time of enhancement factor. So they should be as close as possible, but not touching. That means, say, less than 5 nanometers. But for the practical applications, 100 nanometers is too big. We have to go for a very small particles because always the sharp edges will confine the LSPR too much. Means the SPR very well. So here we have given the enhancement factor calculation. For calculating enhancement factor, you have to have the intensity of sets, intensity of normal Raman, and the number of molecules exposed to the normal Raman, and number of molecules exposed to the sets. So it is nothing but simply, molecule number of molecule normalized intensity has to be taken as a ratio. And there were several substrates developed here. Like you can see many, the very initial developments were on the roughened substrates like electrochemically roughened gold, silver, and so on. Later, people started to use nanoparticles to get much uniformity on the surface and much precise nanoscopic roughness, like metal nanospheres, something like rod, or some physical methods like lithography, nanosphere lithography, and these two are nanosphere lithography, and they also try to grow some well-aligned nano wires to use for this for this application. And you can also find some of the publications claim that it's NERS, nanoparticle enhanced Raman spectroscopy, but it is not widely used. All these methods have been brought under the same umbrella of CERS. And we were also talking about the nano gap. We said we should have a finite distance between the nanoparticles. If it is not, what will happen? So that's what they have simulated here. If you see the first two, A and C, are gap mode, and B and D are non-gap mode. If you go for don't go with this brightness. Yes, here it looks too brighter, but you have to see the scale here. If you go for the gap mode, the intensity goes all the way to 1875. The complete scale is for 1875, but for the non-gap mode, it is just 5.3. And even here they have found a trend with the refractive index. With one refractive index, it is for air. For air, they found almost 1,800 enhancement factor, but for air with the no gap or non-gap mode, it is just 5. And it is also important to note that these when two nanoparticles interact, they will produce surface plasmon coupling. Yes, locally LSPR coupling, I mean. And also this LSPR coupled region is called a hotspot. And from the center of this hotspot, when you go away, the enhancement factor drops drastically. Just consider this as a 10 nanometer particle from this center. If you go to the edge from 10 power 8 to, you are ending up with 10 power 5, or somewhere here it will be very less, like 10 power 2 or 10 power 1, something like that. So it will be very less. So this also has to be considered while we are talking about the heterogeneity of the field enhancement. Actually, this type of drop in field has some applications. I'll come to those concept later. Now let's discuss about some of the aspects about the cell substrate fabrication. Generally, the cell substrate fabrication can be classified into 3 parts: the chemical method, where they synthesize the nanoparticles chemically and deposit on some substrate. Generally, they will go for colloidal dispersion of nanoparticles, and they have also functionalized with some moieties for same kind of, self-assembled monolayer kind of structures here, whatever you are seeing in the first image. And physical methods are that includes like deposition, say physical deposition with the templates, or even lithography and so on. And electrochemical, the physical deposition you can see here in the third image. It's a lithography based pattern of gold for assets application. The third one is electrochemical method. For the electrochemical method, they use template assisted electrode deposition, or electrochemical leaching, or electrochemical etching, redox based deposition, and so on can be used for this substrate fabrication. You can see here, this is actually template assisted deposition, where they used titanium nanoporous membrane, whatever you call anodized alumina kind of stuff. They used here as a template, and they have deposited, I think it's a silver nanoparticles. And we have seen the methods. How about the morphology? Already we have seen we have to have a very sharp edges to have a higher electric field enhancement. For the rod-like structure, you are seeing very high enhancement here, but not on the surfaces. But while you see the sphere, totally you are getting very less enhancement. And while you go for a prism or triangle like structure, on the vertices you will have very high enhancement, but on the surface you will have less enhancement. So let's discuss some of the applications of these CES substrates. The first one I would like to discuss is whole cell sets. That means you can map a living cell using sets. That is possible. Here, of course, there are a lot of work has been done on this. Here they have used to distinguish two different breast cancer cell lines, like MDA MV231 and MCF7. These are the two cell lines they have taken, and they want to distinguish this. How can we distinguish this? Each cell lines have different ratio of UPAR and EGFR proteins. So if you are biomarkers, if you wanted to distinguish these two cells, you have to find out the UPAR and EGFR concentration in this cell, or you can at least try to find the ratio of these two. For that, they took a gold nanoparticle, and then they put a Raman active dye as a reporter. Here it's NTP nitrothiophonol, and then they also used DATT, two different. And after functionalization, they capped with TEPSA and Ampexylane protector to make these nanoparticles biocompatible. And then they anchored with a peptide that is specific to UPAR or a peptide that is specific to EGFR. So now the particle is ready. Now they give this particle to the living cell. When it is swallowing, it will be inside the cell and it will not affect the cell because already we made it biocompatible. So because of the attached UPAR peptides or EGFR peptide, specific peptides, they will absorb UPAR and EGFR. When they are absorbed, these Raman active probes will be segregated at some point, at some locations. Say they have taken a living cell and they gave the mixture of these two to the cell. Now, because this cell has both UPAR and EGFR, the complete UPAR, the nanoparticles have been distributed, but at two different ratios. For example, in the image 1, the EGFR has been distributed in this pattern. In the image 2, the UPAR particles have been distributed in this pattern. So totally you will get this image. Now, let's go for the real problem. You wanted to distinguish these two breast cancer cell lines. So for the MB 321, they got two different mappings. So where you have a higher UPAR ratio compared to EGFR. But when you go for MCF7, the UPAR and the EGFR ratios are almost same, but quantitatively the EGFR concentration is slightly higher. So numerically, if you wanted to see here, for the MDA cell line, it is 1.8 times the ratio. And for the MCF cell line, it is 0.48 times. So this actually gives, it's a ratiometric strategy. So you will not have any external reference because it has an internal reference, or each one is reference to another one. Like UPAR is reference to EGFR and EGFR is reference to UPAR. So because it is a ratiometric, you can clearly differentiate a particle, I mean a cell line compared to another one. And another biological application here is a sensor. It's called immunosensor. They wanted to determine, or they wanted to find an antigen that is specific to hepatitis B virus. So it's called HBsAg antigen. They wanted to detect this in our biological fluid like serum. So what they have done is they just took a metallic substrate, functionalized it with some thiol, which is an anchoring molecule, and then they immobilized the antibody that is specific to HBsAg. So now you have antibodies here. You also have some unsaturated anchors. So you have to put BSA, bovine serum albumin, to block all these unsaturated linkers, which may lead to non-specific binding at the end. So the substrate is ready. Now they are they made the tags. The tag is made like they took a gold nanoparticle and they functionalize it with some captosuccinic acid, and then the anchor is linked with fustian. It's a dye, Raman active dye, and then they attached an antibody on it. So now we have a substrate and the reporter. Let's take the practical application. When you put the biological sample here, it's a linear flow or strip-like structure. So you will you just put it put your biological sample here. It will go all the way here where you have the reporter molecules. If you have any antigen corresponding to the hepatitis B virus, then those antigens will take these reporters and it will go all the way here. This is detection chamber where you will you have already the substrate functionalized with the antibody. So the antibody, once again here antibody will be sandwiched with the antigen. So this is called a sandwich type detector. So here, whatever if you don't have any reporter, or if you don't have any cis active material in this, you will get this spectrum. But because if you don't have any antigen, then obviously these reporters will not reach here. So in that case, you will get a spectrum of the native antibody and all these linker molecules. Once you get the reporter into this chamber, you will get a very strong signal corresponding to the fusion, which has very good scattering cross section, and it will give very high Raman intensity. And because of the presence of gold nanoparticle, it also works as a set substrate, and that enhances the signal intensity further. And with this method, they went up to 0.01 unit per ml, that is international unit per ml detection limit, and with the RSD limit of less than 10%, which is competitive to ELISA, if I'm right. And as we already discussed, the very primary advantage of CERS is its signal enhancement as high as 10 power 8 times practically. Can we use this to detect a single molecule? If you can detect, or if you can if you can monitor a single molecule under simulated conditions, then obviously you have a lot of potentials to understand the nanoscopic world of organic molecules or biomolecules. So for that, since we have 10 power 8 times enhancement, and if your molecule has scattering cross section of somewhere close to the native scattering cross section should be somewhere close to 10 power minus 25 centimeter square per centimeter square per square, then obviously you can detect a single molecule. Say, let's take rhodamine 6G. It has a scattering cross section of 10 power minus 24 centimeter square per square. So because of it's already in 10 power minus 24. If you are adding the enhancement factor of 10 power 8, then you are end up with the 10 power minus 16 centimeter square per square molecule. So in that case, you will be able to detect a single molecule. So this is theoretical. It was, though the CERS was invented in 1974, and it was completely explained in 1977. It was only in 1997 they could achieve a single molecule detection using CERS. They used rhodamine 6G for that, and they used a gold substrate. And if you find here, they have mapped it first of all, and then they analyzed this image. If you see the mapping at the line A with the position, it is they have said in terms of pixel number. If you start from here to here, you are seeing all the fluorescence spots. But when you are scanning from here to here, you are seeing a very clear Raman signal, which is also counting a fluorescence signal here, because here you have a nanocluster. So because of this nanocluster, you are getting a very strong Raman signal. And there are also other techniques like using a Marangoni convection to bring the molecule very close to the hotspot, because as I already said, the hotspot enhancement factor will be very high at the center. When you go away from, you will rapidly drop the enhancement factor. So because of that, they wanted to push the molecules towards the hotspot center. For that, they used the Marangoni convection, where because of the surface tension difference, the molecules will be pushed towards one point. So they used metallic substrates with silica microsphere. These two will have two different surface tension, so you will get a very high concentration here. Finally, they end up with they got a 10 power 10 enhancement factor. It's not 10, it's 10 power 10 enhancement factor. Okay, already we have the method to find a single single molecule using CERS. What we can do? We can find out its chemical or electrochemical properties under simulated conditions. So Professor Van Duyn from Northwestern University, I think this is from Professor Eric from New Zealand. They have tried to probe a single molecule of Nile blue they identified, and then they did electrochemistry on that. So for that, they used the nanoparticle substrate, and then they went for the electrochemical scanning here, starting from minus 0.54 to minus 0.07 volt, where you are seeing the oxidation and reduction peaks of Nile blue. So this is the black curve is for bulk. So you have a bulk spectrum. It tells you that the molecules oxidation and reduction potentials are somewhere here. For example, for oxidation, it is somewhere close to minus 0.3, and the reduction happens almost at minus 0.4. But the peak has its own full width half maxima. It is not a sharp line. Theoretically, it should be a sharp line, but you are not getting sharp line. It is just like a broadened peak. What does it mean, first of all? A broadened peak, of course, it may have its own instrumental broadening, but it cannot be completely attributed to the instrumental broadening. So what they have done is they found out several single molecule events, single NB events. What you are seeing here is they found several single molecule events, and for each single molecule, they found the electrochemistry of electrochemistry in this potential range. So whatever you are seeing, the red curves are oxidation, the blue curves are reduction for a single molecule. So they averaged it over for this potential it is 9 molecules, and for this potential it's 5 molecules. That means this many number of molecules have oxidized at this position. That means even at this 0.4, I mean minus 0.4, there are finite number of molecules oxidizing, and the maximum is somewhere at around minus 0.2. So that is the reason why you are getting the distribution. Similarly, for the reduction, once again you are getting a distribution, and where the maxima is at minus 0.3. It's almost, of course, for the oxidation it is fetching very well, but for the reduction it is somewhat deviating, since it is for the bulk molecule, like nothing but several thousand, an ensemble of several thousands of molecules. So you are getting the average, and the peaks are very smooth in nature. And secondly, how did they confirm whether it is a single molecule or a molecular ensemble? If you say many molecule or molecular ensemble with potential, you will get this is for the stress intensity. So when you start oxidizing, different molecules will start oxidizing at different potential, isn't it? So they started oxidizing. They got something like a peak. It's not a Gaussian, but just a Gaussian-like peak has been given. But when you go for a single molecule, you will get a very sharp jump from the baseline to very sharp jump, and then drop it here. So this kind of behavior tells you it is a single molecule. It's not an ensemble. It's most probably a single molecule. That's what I can tell. But they are claiming it. They are all single molecule events. And with this study, obviously, we can very clearly accept that using cells, you can detect a single molecule, and then you can probe its behavior in a simulated environment like electrochemical or chemical environment throughout its reaction happening, maybe for a period of several seconds, even minutes. It's possible. Here they have probed for several seconds. And another example for this in situ electrochemical sets measurement is monitoring a redox states. In this study, they have taken hydroxylated PDOT, and they deposited on a substrate which has gold nanoparticles. So generally, it is in reduction form. While you apply potential, it goes for oxidized form. So whatever I'm talking is here. So it is in reduction form, and it goes oxidized form. And when you put external external factors like reducing agent and so on, it will once again go for reduced form. It can be electrochemically oxidized reduced or chemically oxidized reduced. That is possible. First of all, they took the the bulk material, bulk thin film of hydroxylated PEDOT, and they have applied potential from starting from 0 to 0. I mean minus 0.5 to 0.5. So you can clearly see it is going up and down, up and down. That means whatever you are seeing here, when it is in reduced form, you will get higher intensity. When it is in oxidized form, the intensity will go down. So that is what for the bulk of the hydroxylated PEDOT you can climb up. So you are seeing a wavy like peak intensity for this oxidation and reduction equation, oxidation reduction reactions. Is it because of oxidation reduction? To confirm that, they also took MBA, mercaptobenzoic acid, and they have applied the potential from starting from 0 to 0.5 and back, and they did not observe anything because there was no oxidation and no reduction in this potential range. Because of that, they attribute this to oxidation reduction rather than potential induced adsorption desorption. Of course, potential induced absorption desorption also can increase intensity, but in this case, it is not happening so far. So where can we apply this? Do we have any practical application? The same group has proposed a sensor application for this. For example, you have a reduced form of hydroxylated PEDOT, and just use H2O2 peroxide, and it will be oxidized. So in CERS, you have higher intensity here. Here it is lower intensity. This can be used as a peroxide sensor. And once again, you just apply potential to reduce. So you're electrochemically regenerating. Just use for other analyte. Once again, it is oxidized. You will get lower intensity. You can reduce or regenerate the substrate using electrochemical method, and once again you can use it for some other oxidizing agent. You no need to go for the reduction by electrochemical. You can also use some other material for reducing agents, or even you can use the oxidized form to send some reducing agents. So that is also possible. So this technology has applications in sensors. And another form of CERS is called shiners. This is one of the important invention by Professor Zq Tian from Xiamen University. We have already discussed about the substrate, how it should be. We claimed that there should be a nano gap between two particles. Everything is fine. How can we maintain this nano gap between two particles? What is nano gap? It should be less than 5 nanometers. How can we maintain this? If you are putting nanoparticles together, they will go for aggregation. The aggregation is nothing but a physical interaction of particles together. So in that case, it's very difficult to control the nano gaps. So what this group has done is they put a silica layer on it, silica layer on these nanoparticles. If you are concerned about the chemical enhancement, which counts around 100 times, while the electrochemical enhancement, which counts around 10 power 8 times, you can also put a porous silica. It's not a big problem, but they put silica or alumina layer on gold nanoparticle. You can see here in this TEM image, where in SEM image you are seeing a very nice particulate arrangements, but in TEM image you can see a very thin layer around 2 nanometer, and they also synthesized with a different layer thickness. And we'll see what happens while you have very high thickness. Just in this spectrum, whatever you are seeing here is a platinum oxidation. So they took a platinum surface. On that, they put these shiners particles. Shiners is nothing but shell isolated nanoparticle enhanced Raman spectroscopy. So shiners particles. And then they wanted to, they studied the platinum hybridization, PTH formation. If you see, the fourth curve here, only PT111, where they formed actually PTH, but with Raman they did not find any peak. And while you go for PT111 with the hybridization, they have, when they put a particle with very very thick shells, like 20 nanometer, whatever they have synthesized here has 20 nanometer thickness shell, they did not find any Raman signal for PTH. Then they went with the thin layer on PT substrate. Then they started to see the PTH vibration in Raman spectrum with a different potential starting from -1.9 to -1.2. They gradually see the intensity increase in the Raman spectrum. And this is for SiO2 layer, and for the alumina layer also they got the similar trend. And they proposed an application for this technique on pesticide detection on citrus fruit, say from the top to bottom. Here we have the spectrum for only orange, and the top one is the spectrum for the bulk spectrum for only the methyl parathion pesticide. So when you put a methyl parathion on this citrus fruit, you obviously expect a peak here. But in Raman spectrum, it was not appearing here because of the sensitivity. Obviously, the citrus fruit skin has a lot of chemical, it's its own organic molecules, so you get these two peaks only. When you put these shiners particles on this substrate, they got this peak for methyl parathion. So this is the sensitivity, and this is the beauty of this technology on practical applications. Once again, the same group has proposed another application for this. Like they have probed a complete reaction, starting from its precursors. Saying at the end they got some products. Completely, they have probed reaction. Here, in this case, they have probed oxidation of carbon monoxide. Carbon monoxide reacting with oxygen, they form carbon dioxide on PTFE substrate. They used this shiners for stress enhancement, and they have the electrochemical, they have the stress substrate. When the carbon monoxide comes in and reacts with oxygen to form carbon dioxide, they will have some surface reactions, right? They have completely studied, but I'm showing here one example only. Like if you see here, if you see only PTFE with silica, some people may claim silica would have absorbed all these carbon monoxide, oxygen, and carbon dioxide. Because of that, the peak emerges. It is not. Why? Because for PTFE on silica, it didn't show any peak. PT on silica, once again, it didn't show any peak. The shines, the shell-isolated nanoparticles, that also shows no signal of this. But once you have PTFE, that is a catalyst, and shines, that is for stress enhancement, if both together exist, if you allow carbon monoxide and carbon oxygen, then you will get a very strong peak corresponding to PTC. That is the primary rate determining step for carbon monoxide oxidation. And this is one of the example. They have there are so many other electrocatalytic reactions have been probed using this method, and nothing but you're probing the intermediate steps as well as intermediate species. Another example for this shiners is in lithium-ion battery, where they use NMC catalyst as an anode. So they formed a spectroelectrochemical shell. In that shell, you have a spacer, lithium foil as a cathode, and separator, and NMC composite electrode as anode. So they wanted to probe what happens to the NMC electrode when you go for cyclic study. What happens? Why it is? What's happening? Whether if it is dying, why it is dying? All these things they want to probe it. So for that, they formed a cell like this, and they
the feedback link feedback link
excuse me. Hello, am I audible, sir? Hello. Hello.
Sir, audible, sir.
Okay, so
Yes.
someone was talking, so I thought I'm not audible. Fine. Okay, and I'm just continuing. So when they probe the NMC catalyst from the top, when the potential is with OCV, open circuit potential, they got this spectrum. So that's what you are seeing here. This is the native spectrum of NMC 11H. So when you scan the potential from OCV to 4.8 volt, you are seeing at some of the peaks have emerged quite strongly. So these peaks have been attributed to the cobalt oxide and the nickel oxide rock salt. It is in rock salt structure, and it is in spinel structure. So these two have been emerged. That means the NMC catalyst is nothing but lithium, nickel, manganese, cobalt oxide. So the manganese, I'm sorry, the nickel and the cobalt have been oxidized to release into the electrolyte. This is happening because of the electrolyte oxidation. The electrolyte oxidizes, and it the oxidized form releases oxygen, and that oxygen reacts with the substrate NMC catalyst, and it forms some islands of NiO or cobalt oxide. So that has been probed completely with this in situ CERS method, I mean in situ Shiner's method. And compared to NMC 811, NMC 111 was performing better. Why? Because when compared to the emergence of this peak, here the emergence of the peaks here is not that significant compared to this. So of course the NiO or the NiO or cobalt oxide formation is there, but to different degrees for NMC 111 and NMC 811. So this has been probed using in situ Shiners with electrochemistry. And we have seen some aspects of CERS substrates and its fabrication and its applications, its capacity of detecting a single molecule and monitoring throughout reaction. Everything has been we have discussed. And another derivative of CERS is TERS, tip enhanced Raman spectroscopy. In tip enhanced Raman spectroscopy, the complete theory is same. But in CERS, you have enhancement factor as high as 10 power 10 or practically 10 power 8. But what about the lateral resolution? If you have say 1 micrometer square substrate, 1 micrometer square area, if you are mapping that, will you get the same enhancement throughout? You will not. Why? Because in the hotspot, I have already explained here, if you have two particles and they are interacting through LSPR, then the enhancement factor will fall very rapidly from the tip, I mean from the hotspot center. So this is a very big limitation. People are thinking it is a very big limitation, but it is not. It was a big opportunity. Why? Because if you have a very if you have a surface with very high angle of curvature, then obviously you will have the very gradual drop in enhancement factor. But what if you make it very sharp? If you make it very sharp like this, like a tip, then from here to here, the enhancement factor drop will be very high. If it is making very high, then if you are using this tip, if you're using this as a tip for mapping laterally, then your interference from one pixel to other pixel is very less. So that has been taken into advantage, and they have developed a technology called tip enhanced Raman spectroscopy. And here, the sharper the tip will give you better the lateral resolution. And if you see a comparative chart, if you see all the spectroscopy methods like spectrophotometry or Raman and so on, CERS, including CERS, XPS and so on, they will give you very good chemical information, but not a good lateral resolution. If you go for same kind of microscopy methods, electron microscopy or probe microscopy, anything, they will give you a very good lateral resolution, but not chemical information. But a test gives both of them. That is why it is superior here. We'll see some of the aspects of the TERS. In TERS, the very important requirement here is your scanning probe as well as the laser probe. Both has to be synchronized. These two should touch locations simultaneously. So when the probe is very close, like it should be away from just 1 or 2 nanometers, and your light also, I mean laser probe, generally it will be 25 or 50 micron in size. They also should touch the same point. So it should be completely synchronized. When it is achieved, you will get the scattered, that means excitation wavelength and then scattered wavelength, both you will get. It will be in the scattering mode as well as in the transmission mode. It is really not a transmission, but scattering is obviously, you know, scattering is isotropic. So you will get scattering all the sites. So you will get a transmission also. So you can use the transmitted geometry also for TERS. So here you are seeing different geometries used for TERS analysis. This is the transmission geometry where your tip will be on the top and your Raman probe, I mean the laser probe will be at the bottom. These two will be synchronized to move X, Y to scan the matrix. And here, this is top model where the top, the perpendicular position is used for tip, and a 45-degree angle is used for your laser probe. In this case, generally there will be some limitations, like whenever you scatter with photons, you will get more intensity somewhere here, and because of that the signal intensity will be limited here. And they also went with some other geometry like this. This is very common geometry. You can see many work on this one. You will have a perpendicular laser probe and a 45-degree or 30-degree angle I mean TERS probe. And you can also go for this kind of method where you will have dual source and dual detector. This is nothing but the symmetry of this method, but you will have some advantages. Whatever the scattering you are losing here will be detected by this detector, and whatever you are losing by this one will be detected here. So this in this method, of course, you will get better resolution, but the problem is the complicated geometry. But this one is very common. You can see many group are working on this geometry. And how about the probes? Of course, as I already said, the sharper the probe, you will get better the lateral resolution. And people have a different method to produce that. You can also produce a sharp tip using some other non-plasmonic materials like silicon, and then you can coat plasmonic particles on this, because producing a plasmonic tip as sharp as like silicon is it has some limitations. So in that case, you can produce a sharp tip with non-plasmonic or silicon-like structure, and then you can coat metallic nanoparticle on this to get a plasmonic surface in the tip. And of course, I have already said it should be sharp enough. And there are different methods used for producing these sharp tips. The first one is electrochemical etching, where they take silver wire and they use a ring-like counter electrode. Because of this ring-like nature, the uniform potential field will be produced, and that will sharpen the tip when it is pulled out. And they got sharpness in a nanometer scale. And as I already said, you can also use silicon tips where you can coat gold on this by some deposition methods. So once again, you get a sharp one, but it won't be sharp enough like this, but still you can use it for test analysis. And the third method is the pulling. You can use you can heat locally a metallic wire, and you can pull it when it is heated to its melting point. You can pull it. You can use thermal or laser to heat the metal at the local point, and you can pull it to get it very sharp enough. So they also use the metal wires with very minute thickness, like say 25 micron or even less, cannot be mechanically stable. So for that, they support it with glasses. So it will be like a coaxial structure where the core will be your metallic wire, and the sheath will be glass. So glass will give you glass will give you a mechanical strength, and the core metal will be used for plasmonic enhancement. So this is a typical one produced by some company. And now let's see some of the examples for this test. What about the sub-nanometer resolution in chemical imaging? So, of course, you can get TEM images with sub-nanometer resolution, but if you wanted to map a substrate with sub-nanometer level resolution, you have to go for TEM, or if it is in probe microscopy, then you can go for STM if it is a conductive substrate. But what if you don't? If you want the chemical information also? They will give only morphology, but if you want chemical information, then obviously you have to go for TIRS. In this example, they have two molecules. One is metal-centered, another one is free base. So it will not have any center. So here it is a zinc center. This is not a zinc center. Or both are porphyrins. So they coated these two porphyrins on a same substrate, which will make a clear boundary here. So whatever you are seeing here is a morphological mapping. So here you have one element, and here you have another element. So it clearly tells you, because it has zinc center, it gives you different resolution. So because of that, you are seeing two different surface topography here. And while you go for more, say, higher magnification, you are seeing this kind of image. But what about the chemical information? Just come here. Here, the blue red is for the zinc-based porphyrin. Another one is for the free base porphyrin. So you are seeing a clear mapping difference. The color difference is because of the two different peak mappings. I think they used this 701 and 918 for mapping these two. 701 for this one and 918 for this one. And this mapping gives you a clear chemical information which is distributed over a lateral dimension of almost 10 square nanometer. So this type of techniques can give you not only the morphology, topography, and also will give you the chemical distribution information. And when they went for a very high magnification, like with very high resolution, like 0.4 nanometer, they could even see the core and the lobes, the molecular core. This is molecular core, and whatever the benzene rings you have here is molecular lobes. So they could even image the two different images for the molecular core and the molecular lobes. Whatever you are seeing here is the simulated image for molecular lobes, and experimentally they got very close to that. And the simulated image for the molecular core, that also they got very close to that. So in this, you are seeing the Raman spectrum of a single molecule at two different locations. That means intermolecular segments could be imaged using this method. And a similar for the copper copper based, copper thalocyanine also has been done. You can see it's a very low magnification image. Whatever the arrangements you are seeing is the molecular arrangement. While you go for higher magnification, you are actually seeing a single molecule here. They are arranged into a kind of crystal, lattice like a crystal. This is on AG111 substrate. It's a copper thalocyanine add layer on AG111 substrate. They also used AG tip to map it. So when they map it, in fact, whatever you are seeing here is almost 200 nanometer, but this tip, I don't know whether this is sufficient, but they just showed it for example, I guess. But with this tip, they got a very good resolution between the molecules. So whatever the molecular arrangement, whatever here you are seeing a scale of 1 nanometer. So you could see two molecules which are separated by sub-nanometer level separations. That could be clearly seen here. And also they have tried to map the molecular structure with this arrangement. And here they have okay, once again they are mapping the molecule, and they also got the spectrum to confirm that they took the image when the probe is engaged as well as retracted. The difference gives you the spectrum of the molecule whatever you have taken here, the copper thalocyanine. And based on the spectrum obtained from this spectrum, whatever you are seeing here, from this spectrum, they have calculated the differential scattering cross section, and they found it to be in the order of almost 10 power minus 27 centimeters square per square. Thanks. The differential scattering cross section is around 10 power minus 27 centimeters square per square. And this is another and final example of tests where they probed the Nile blues, the Nile blue dye. They took Nile blue dye, and when they reduce or oxidize, what will happen? So they used it for a single molecule electrochemistry. The test-based single molecule electrochemistry. If you see here, you have, of course, they have compared it with CERS also. So in the oxidized form, you have different spectrum, and in the reduced form, you have different spectrum. Both are giving, in CERS as well as TERS, they are giving same signal. Here in this second spectrum, they have done a bulk analysis where they took reduced form of Nile blue and oxidized form of Nile blue. They have taken two different spectrum, and while it is in reduced form, they have an additional peak at 1376. But while you go for in situ electrochemistry, obviously both the phases will exist. So in situ tests, they got both the peak for both the phases. And similarly, the same kind of the same kind of pattern has been obtained here. Another group tried to probe the electrochemistry of 4B PBT absorbed on AU111 surface and the AU nanoparticle surface also. Let's see what will be different. If you take AU nanoparticles, you have to consider it as a CERS substrate, and there will be no test probe used. And if you take AU111 surface, the substrate is AU111, and then you will use AU tip also. So you can see here there are two peaks, and sorry. In 4PBB, I didn't give you the molecular structure. It will give you, it will have the pyridine ring as well as the benzene ring. So pyridine ring gives 1592 peak, and the benzene ring gives you 1605 peak. So if you see in CERS, these two peaks could not be distinguished. They are, it doesn't mean that it is not giving, but it gives. They are clubbed together. It is not resolvable because of the large area where you are getting the signal over CERS probe of 1 micron diameter or even more. But whatever the TERS probe you have is of nanometer scale resolution. Because of the high resolution, you are actually probing a single molecule where you can clearly see the pyridine ring as well as the benzene ring separately. So that's why you are getting a two peak here, and which is not resolvable here. And this is one of the important with the different potentials. You initially you will get two different rings, and when you increase the potential to minus 700 millivolt, then this peak started decreasing because of the hydroprotonation of this pyridine ring, and that is not resolvable in sets. So this study gives you an idea how superior the TERS compared to sets. And in the summary, obviously, the plasmon-assisted Raman spectroscopy has potential as high as detection of single molecule and monitoring its electrochemical or chemical events throughout a period of time. And you also, because of its high potential, there are several derivatives of sets has been developed so far, like scanning. SCRRS, resonant Raman spectroscopy, surface enhanced resonant Raman spectroscopy, surface offset sets, or graphene enhanced Raman spectroscopy. PERS has, even in PERS, you have three different abbreviations: plasma enhanced, or probe enhanced, nano, or Pluxiton enhanced. So there is a lot of methods developed in the last 1 decade. So they have to be standardized, and they have application in catalysis and sensing because they have potential to detect as low as single molecule. And also the instrumentation of these methods are a little more complicated. So this gives you a potential scope for developing a simplified instrumentation, and you can also go for a standardization, and you can also develop new methods to detect catalysis, detect catalytic intermediates, or detecting biological molecules in trace level. You can also even develop new enhanced Raman spectroscopy techniques. So there is a lot of scope in this that you can also hyphenate it with other techniques, like already it has been hyphenated with electrochemistry. Why not with other techniques? So there is a lot of scope for this method. So I encourage people to look into this kind of advanced spectroscopy, and obviously the plasmon-assisted Raman spectroscopy opens a new era in spectral analytical techniques. And I welcome you all. And thank you for your attention.
Now it is the time for open discussion. Dear participants, please post your questions on the chat box. Our resources one will answer your questions.
So should I go with parallel answering?
Yes, sir.
I'm also seeing already 37. Okay.
So one participant asked the question, sir.
Okay.
Which organic solvent can be used in Raman spectroscopy? Is it environment friendly?
Organic solvent for Raman spectroscopy, I didn't get because in Raman spectroscopy, in general, you will go for dry powders, or if you wanted to do solvent solution based one, and obviously you have to go with whatever the solvent you wanted to use. But there is no restriction because for Raman, you will use micrograms of samples only. So that is not a big problem.
The next question, sir. Why do we get a noise with the Raman spectroscopy with no light source?
With no light source, indeed, see, if you see Raman spectrometer, that you will have say a grating, and whatever the light you are putting is monochromatic, but you put monochromatic, but at the end you will get a light with a different wavelength. So whatever the wavelength you have used for incident, you will filter it out, and whatever which is not matching with your incident light, it will be given to your grating. The grating will disperse, and wherever you have higher intensity, you will get a peak. That is Fourier transformed. So that only you will get like a peak structure. But if you don't have any light, that means if you don't have any laser, then your CCD will just take some background values, because each instrument has its own background value. Okay, so that background value will be just showing like just jumping like here and there. So you will see no peak structure, unless otherwise you have a very clear distribution like Gaussian or Lorentzian distribution. You should not claim it as a peak. So that's just a noise.
Any more question from the participants? So if there is no questions, means we come to the end of session. It is a time for formal vote of thanks.
Thank you. And before that, I just I think in the chat box. Oh, noise. That's what you asked. Okay, fine. I'm seeing from Abbas. What is organic solvent? Okay, organic solvent related question. And is there any other analysis method one can do to analyze Raman spectroscopy data other than stacking the plot? No, stacking the plot is just a representation. You just go for a peak analysis. Like first of all, you have to deconvolute if the peaks are convoluted, and then you have to fit with either Gaussian or Lorentzian with the minimum gamma value. And based on the peak position and whatever your expectation, if the peak is blue shifted or red shifted, then obviously you will have a lot of information to be derived back. And the full width half maximum is also playing a lot of role in your Raman spectrum. So just stacking will give you the peak position information. Like for the raw material, it was in some position because of your treatment, it is shifted, red shifted, blue shifted. That is not only the information you are going to get in Raman spectroscopy, you can get a lot more information. Particularly when you are comparing 2 or 3 different spectrum, you have to compare the relative intensity, not the absolute intensity. Unless otherwise it is taken on the same location, like if you go for time resolved Raman spectroscopy, then it's not a big problem. You can compare one spectrum with another one. But if you are comparing the spectrum of 2 or 3 materials, then obviously you have to go for relative intensity rather than absolute intensity. And thank you all for your appreciation. And if you have any other question, I'm happy to answer. Otherwise, thank you all for your attention. And over to Professor Sheikh.
It's a time for formal vote of thanks. I would like to thank our today's resource person, Dr. P. Tamilarasan, scientist, CSIR, Sikri, Karaikudi, for delivering a wonderful lecture on Raman spectroscopy. So in his lecture, he pointed out important concepts of Raman spectroscopy for structural characterization. It was very useful and informative, sir. Thank you very much for your nice presentation. Thank you, sir.
Thank you very much. Thank you everyone for your attention, and meet you soon in another event. Thank you.
Next, I thank all the participants for participating in this FDB program. So next I thank Mr. Kannan, who made all the technical support for successful conduct of this FDB program. So next, I thank all the participants once again. We meet you tomorrow. Thank you, one and all.
Thank you.
Thank
Have a
you,
good
sir.
evening.
Thank you, sir.